All right, let's look at an example. This is from a FRQ, free response question from the APTS. So it says at time greater than or equal to 0, the position of the particle moves along curve in the xy plane with x of t, y of t as its vector, position vector, where the derivative of dx dt is shown, and same with dy dt. At a time of 3, the particle's position is negative 1, 2. Write an equation for the tangent line of the particle at time 3. Okay, so if we want at time 3 here, we're given some information that's very useful. We know that at a time of 3 here, the position is shown. So that's our point, but we need the slope. What's the slope here? Well, that slope has to be our dy dt, or sorry, dy dx here. And we know from previously working with this that dy dx is going to be our dy dt over our dx dt. And those things are given to us, those two equations up here. So we got 6 cosine of 1 plus sine t here, all over t minus 5 cosine t. So now what we got to do is evaluate that at time of 3. So we want to find what is dy dx here when t is 3. So this is just now going to your calculator, and this was a calculator question on the exam. Plug in 3 anywhere. We see a t here. So now just use calculator. Make sure you are in radians and plug this in. So it looks like we get, here, typing this in, we got 6 cosine of, actually, I'm going to restart here. This one is probably going to be better here to enter as a fraction. I'm going to use that fraction shortcut here. So 6 cosine of 1 plus sine of 3. Close up these parentheses here. Let's move to the bottom now. We got 3 minus 5 cosine of 3. And if we hit enter, this should give us the approximation. So remember with this here, round to at least 3 decimal points here, so 0.314. Last thing we need to do now is write this out, write our answer out, because they want equation for the tangent line. So we would have y minus, our y point over there was 2. Our slope is 0.314. And our x value here was minus negative 1. So either that, or if you wanted to simplify that into plus, that would be good enough there to get you credit for that part. All right, next part of the question here. Same information. Find the time t when the line tangent to the path of the particle is vertical. Is the direction of the motion of the particle up or down at that moment? Give your reason. Okay, so if it's vertical, that means our slope is undefined. So with our last part to this one, we found that dy dx was equal to our dy dt, which was this, over our dx dt, which was this. So if it's vertical, when it's vertical, that means the slope is undefined. So that would be set, we'd want to set denominator equal to 0. And solve that. That would give us the time that that's going to happen. So what you'd want to show is when does this equal 0? Now, solving that's not easy, and what they expect, because we have the calculators, that you'd use calculator to figure this out. So what you'd want to do is use the graphing feature of your calculator to do it. And for this case, my calculator right now is in the parametric mode. I think for this we'd want to go back to function mode. Would be easier. So let's graph this one out. I'm going to clear out these other functions I had in there. So we want to graph, and it doesn't matter that's not t in here, x minus 5 cosine x. Do make sure you are in radians here. And we want to see where this equals 0. So once we graph it, here's the graph. Now remember, for this problem here, it's where t is greater than 0. So anything to the left of 0 we don't care about. We're only interested in to the right. So the point we're trying to find is this one right here. So what we got to do, use your calculate feature. We want to find where's that 0, because we want to know when is it equal to 0. They want to point to the left. It looks like it's somewhere between 1 and 2, so I'm just going to hit 1, enter. Point to the right would be 2, enter. Guess, you got to hit enter one more time, and they give it to you. So the time here is approximately 1.306. Okay, so that's part of the answer. The other part is the direction of the particle, the motion moving up or down at that moment. Okay, so what you have to use to answer that, the part that's going to tell you up or down, that's the dy dt here. So you want to now plug that time in for dy dt to figure this out. So dy dt, we're going to evaluate that at a time of 1.306 and see what we get. So again, that use calculator to do that would be fine, as long as you're showing with notation what you're doing over here. So on your calculator, let's plug this in. So we got 6 cosine of 1 plus sine, and here's where we're putting our answer we just got in 1.306, and looks like it comes out to be about negative 2.305, which is less than 0. And so this object, if it's negative, is the motion is that it is moving downwards, and that would be enough to show for your reason here why it is, because it's less than 0, it's moving down. All right, let's keep rolling with this. Part C, find the y coordinate of the particle's position at time 0. Okay, so to find the position at 0, we need to use a location that we know, and we know at 3 that this is the position. So we want to use fundamental theorem of calculus to do this here. So if we did an integral from 0 to 3 and integrated the velocity in the upward y position here, so our dy dt, then what we would get would be the y position at 3 minus the y position at 0. The one we're trying to solve here is the one at 0. So I'm going to just rearrange this equation a little bit here then. Y at 0 would end up being our position at 3 minus our integral value for this. Okay, we know the position at 3. The position at 3 in the y position here is 2. And then what we're going to do is this part we're going to use calculator to evaluate. So let's jump on our calculator here. We should be able to do that integral here. So go math, do our integral here from 0 to 3. and then type in that dy dt function, so 6 cosine of 1 plus sine, and it doesn't matter that's not t right here. Let's close those parentheses up, and we got to hit one more x here and hit enter, and this we'll use calculator to find this, so the value comes out to be negative 1.63, we'll round that 634. And so the position then, if you double slash or turn that to adding, would be 3.634. And that would be the position. They don't give us any units for the position, so that would be sufficient for the answer there. All right, there's one last part to this one now. Find the total distance traveled by the particle from 0 to 3. We looked at this in a previous one. If you want total distance traveled, that's going to be the integral from 0 to 3 of that square root of dx dt squared plus dy dt squared. And if we integrate that, that would give us the total distance traveled. You don't need to actually write the functions in. As long as you're showing what you're doing here, that would be sufficient. And now again, use your calculator to find this out. So again, do the integral on here, and we can get that. So we'll set up another integral from 0 to 3. And then we're typing this one in, so we want square root first here. Make sure you get a parentheses in here. Type in that dx dt function, so x minus 5 cosine x. You got to close up this parentheses for the x, close up the parentheses that we started. We need this squared. Plus, now start a new parentheses, type in that other one, 6 cosine of 1 plus sine. We got to close up the one for the x, we got to close up the one behind the cosine, and then close the one for that we had started, squared, and finally put the last variable in here, and we should be able to get the distance traveled, which turns out to be about 13.453. So that's an example of an FRQ that has parametrics in it and uses some of the stuff we've been going over in these lessons.